Now, if you're watching this, it's probably because you're not liking your first meeting with differential equations. And at this point, I'd like to say a little hello to a Mr. Zirak, the esteemed Amosi of St. Nins. Anyway, differential equations. An equation which has got one or more derivatives of an unknown function. So, like this example, there's a couple of derivatives in there. There's two main groups of differential equations. There's the ordinary differential equations, which you will do, and they've got just one independent variable. Usually you to use x, but there's other variables you could use. And then there's one dependent variable. That's the function of x that you're trying to find. The other group are the partial differential equations. That's where there's more than one independent variable, and you'll not be doing those. The next characteristic of a differential equation is its order. The order is the highest derivative that's present in it. So in that first example, that was a differential equation of order 3, because the third derivative was there. Notice all the rest don't need to be there, but the third one was there and the first one was there. The actual function itself wasn't present in its own right, but that doesn't matter. It's still a differential equation. Now, in the advanced higher, you only do first and second order differential equations. The next complication you can get in differential equations, so another term here is the degree. Now, the degree doesn't mean which derivative's there, it tells you the powers of those derivatives. Strictly speaking, the degree of a differential equation should be the power that's applied to the highest derivative. But you're mainly concerned with the degree of a differential equation when the degrees are all just 1, when the unknown function, y if you call it that, only appears in its own right, just y, or dy by dx, or whatever derivative of it you have, and there's no powers or signs or anything else. In that case, it's called a linear differential equation. So that very first example was a linear differential equation. So having those three terms then, ordinary differential equation, order and degree, or specifically linear. Here's some examples. This first one is a linear second order differential equation. Nothing appears there squared. The x is not the x's that matter. Those little functions of x are just the coefficients. The coefficients don't just need to be numbers. They don't just need to be constants. They can also be functions of x. But in the advanced higher, when it comes to these second order linear ones, the coefficients of the main terms will just be simple ones, they'll just be numbers. The second one there, that's a linear first order differential equation. Notice the y just appears by itself, it's not being squared or anything. And that last one, that's a first order differential equation, but it's not linear, it's a non-linear first order differential equation. So whereas in the advanced higher you only do linear second order ones, the problem here, and that's the whole point of this I suppose, is with first order ones they might be linear or not linear. Now, the first thing you'll need for it to be a first order one is a first order derivative. And it's easy to tell whether you've got a linear one or not. It'll be linear if y appears just on its own and there's no powers involved. Well, in fact, y doesn't even need to appear at all for it to be a first order linear equation. The full form of it would be something times dy by dx. You call it a constant, but that constant can be a number or a function of x. The important thing is it doesn't involve y. So I'll just call it, for instance, something like p of x. Some number of y, which could just be a number, or a function of x. Call that q, for instance. And the third part would be, you can put it on either side, a term that doesn't involve either of them. That would be the full form for a linear first order ordinary differential equation. Now, these can just be numbers, some of them don't need to be there. The only one that needs to be there is there needs to be some number of dy by dx, or it wouldn't even be first order. But the thing to notice with linear ones are the y just appears as a y if it appears at all. It doesn't need to be there. Q could have been 0, for instance. And I might just have had something like x dy by dx equals, and that doesn't need to be a function of x, it can just be a constant, 2. That's still a linear first order ordinary differential equation, but obviously that's a trivial one. I might as well finish that off. First thing you would do is you'd take the x across, and divide. But notice, as soon as you do that, you've created a limitation. You can only divide by x if x is not equal to 0. So immediately you've limited your solutions now. This is only going to be true now as long as x isn't 0. And then, whereas normally you just say y equals, I might as well do what you're going to do next, which is to split the differentials. Those little parts are called the differential. dy is the differential in y, dx is the differential in x. Those little variables in their own right. So dy would equal, take the dx across, 2 upon x dx, and then you integrate both sides. Now, the integral of d anything just goes to the thing. The integral of du would go to u, dt would go to t. Even if it was more than that, the integral of dxy would go to xy. Whoops. But also plus a constant. But both sides are going to give a constant, so you might as well take the constants over to the one side and have a single constant. That's why you tend not to write it here. Well, in fact, you don't tend not to, you just don't write it there. You just put the net result over here. So that would go to y equals, and here's another thing. That goes to log. When I say log, I mean natural logarithm, but I'm not going to go ln, I'll just say log. 2 ln of x, and then there's a plus c. But now there's another limitation, because this logarithm's a sensitive wee creature. You have to be careful what you feed it. You can't put a negative into it. Remember, the logarithm graph looks like this for x and y. There's no answer to this. It doesn't even have an answer for 0. There's certainly no answers for negative. You can't put a negative number into logarithm. So what you have to do to stop the wee soul exploding is to wrap this x up, put it in a wee straitjacket, as you might call it. So it's the absolute value of x you'd have to put down here. Now, there are times when you don't need that. If, for instance, you know that x is greater than 0, for instance. If I had a condition that says, oh, x is greater than 0, I wouldn't need to do that because it's perfectly safe to feed x into the log. But anyway, that was all just by the by. So that was the first order one where there was no mention of y, so that's just trivial. Right, here's another one. Straight away, it's obvious that's not linear. Look. Y's got power 2 on it. It's only going to be linear if it's just a y term on its own with something multiplying it. Now, the only way that you'll know how to deal with this type, a nonlinear first order differential equation, and you won't meet ones really when this has got power 2 or 3 or 4. It'll just be the y that isn't linear. The only way you can deal with this is if somehow you can bundle these two together. So for instance, I could take that term over as plus 4x cubed y squared and form a factorization. Because if you can turn it into a factor that just involves x and constants times a factor that just involves y's and constants possibly, if you can separate them like that, then when you split your differentials, you can also split them and have one side for the y's and one side for the x's. Just keep them apart and all will be well. Oh, so you have to look at this part and say, can I factorise that? Well, of course you can. That's 4x cubed times 1 plus y squared. There you go. That factor, 4x cubed, just involves x's. This factor just involves y's. Okay, and a number, but that doesn't matter. Now that you've got them separate, you can use the technique of separation. Separable variables. So the dy can stay in that side and the 1 plus y can go and join it. The 4x cubed can stay in that side and cross multiplying it, the dx can join it. You've separated the variables, you've created two separate halves to the problem, so you can carry out two separate integrations. Again, there'll be a constant from here and a constant there. I'm just going to put the net constant down. So that's a nice little up to 4 divided by 4 is x to the power 4 plus a constant. And you should recognise that as inverse tan. That's inverse tan of y is equal to that. And finally, to get y, to get the solution, what's called the general solution, because I've still got an unknown constant c, so you've got a whole load of equations there, if you like, a whole family of them. That would equal tan x to the 4 plus c. for the general solution to this nonlinear first order differential equation. Of course, if you're given a value of x, y, normally called initial conditions, you can work out C for those particular values, and that would be a particular solution. But as it is, I've got a general solution because I've still got this constant in it. So here's another first order differential equation. This time you can see it's linear. Where y is mentioned, it's just y in its own. It's not a y squared, it's not a root y, it's not a y multiplying the divided by dx. It's not a sine of y, it's not a log y, it's not anything, it's just a nice little y. And they're all multiplied by functions of x. Those are the coefficients. They could just be numbers. One of them could be missing. Two of them could be missing. Well, in fact, if they were missing, that would just equal 0. That'd be no use. Well, you could still get an answer. Now, this is the other type. This can't be factorised. I can't take these across, sine x minus 2xy, and then divide by the x squared and somehow get a factorisation that will split them. I can't separate them. This is not separable, so the only way you can do ones that aren't separable are ones that are properly linear, which you recognise straight away because it's only got the one y. Now this is actually an ideal one. This is a perfect first order equation. In fact, you call this type an exact one. The reason being, this side here is exactly the derivative of a product. And the aim in other first order linear differential equations is to multiply, to manipulate it, to try and get this exact form. If you've got some function of x that's made up of a product like px, qx, just to use those names, there don't mean anything here, and you want the derivative of that, then the derivative's formed by doing that twice where each of them takes their turn. So you can either do p dashed x, leave q, and then leave p dashed x and then do the q, and that extends to 3. If it was then pq times, r to the x, there'd be an r to the x which has still got to get its turn done. So that'd be then plus p of x, q of x, and then finally r, where they all take their turn. That's exactly what's happening here then, looking at the parts. Because there's a y, and there's its derivative. So they were one of the pairs. That was the y having its turn. That's the y in its own. So if that's the y having its turn, that must have been the one in its own. So that must be its derivative. That's its derivative, and that's its derivative. So that's a perfect product. That's what you would have got if you differentiated the two originals, the x squared times the y. That's an exact derivative, which you just spot just by looking at it. You just get that by inspection, you realise you've got an exact derivative, there's a product there. And then you can finish it off in that manner, because since that is a differential in its own right, that will just be sine x dx, and when you integrate both sides, that will just go back to x squared y, and that will go to negative cos x plus c. So your answer will be y equals c minus cos x over x squared. You didn't have to do anything because you recognised straight away you had an exact derivative, or rather the exact derivative of a product. So here's another one. That's linear. I can't do any jiggery-pokery by taking this to one side and factorising it. That would always be preferable. Separable's easier than solving a linear first order differential equation by trying to make it exact. But I can't do that here. I can't take that across and divide by x and get anything happening with it, so I'll have to treat it as linear, and it is linear. Y just appears on its own. Well, first thing is it exact? No, not quite. Look, y becomes divided by dx, but x would become a 1. So obviously there is something you could maybe multiply it by, but it's not quite right. If that's the case, and of course in most questions you get that will be the case, it's not going to work, then just divide by the x. So it'll be 1 minus 1 over x. And then you have to think, and the technique is this, what could you do to this to make it exact? what could you multiply it by? There's going to be a multiplying factor that will make it exact, so it could be integrated, and that's what you call the integrating factor, for which you use the symbol mu, mu, mu. That's small m for multiplying, small m in the Greek alphabet. But it's actually a function of x. But quite often you just write mu on its own, just like you write y on its own. Y is actually a function of x, because x is the independent variable and the value of y depends on it. So y is a function of x. You can write that, or you can just write y. But what could you multiply it by? What could I multiply this by? I'll just put it in here and multiply that by, so that forms a product. You get a clue from this actually, because whatever you multiply by has got to appear here and appear here again, unaltered. Now there is something that does that. E to the something, when you differentiate it or when you integrate it, stays that. It stays as e to whatever you've got there. If I put a p of x there, for instance, if I differentiate that, I've still got e to the px. The only thing is it gets multiplied by the derivative of that. Well, that means that would work here then. If that could be the derivative, then if I integrate that, that will tell me the original up here. That makes the multiplying factor. Of course, I'd have to change my terminology here then, so that if that is this, if I want that to turn out to be this part of it, that would have to be the derivative of this, so that must be the integral of that then. That's the integrating factor. Right? And that's the technique you use. Unless it's an obvious one, don't forget, if it's obviously a perfect product to begin with, if it's exact, just do that. Or if it looks like it'll factorise and separate, do that. But if that's not the case and you've got a linear one, then look for this integrating factor. What could I multiply by to make it exact? So I'd start off, you can make these statements, I'll say, well, px is 4 upon x. The integral of 4 upon x dx is equal to, now there's a couple of things here. That is 4 log x, but it's actually 4 log x plus c. And I should really be putting that little modulus sign in as well, so that my integrating factor, whether you call it mu or mu of x, is going to be e to that. Now there's a reason why you can get rid of, in fact in this case there's another reason you get rid of it. When you're going to use this as a multiplying factor, you don't actually need either of those parts. Even if that was, say for instance, e to the whatever, x plus c, if it turned out that was the result of the integration. Remember, you've got a plus c in it. That's the same as e to the x times e to the c. E to the c is just a constant, you could call that a. And you're going to multiply all three parts by it. It'll be a times this, it'll be a times that, it'll be a times that, and those a's would all just cancel out. So that's why when it comes to integrating factors, you don't bother putting the plus c in. It should have been there, but it'll make no difference because it'll just cancel out from the three products. The other thing is, this ln x, well, first of all, in this case it disappears anyway, because there's no point in having e to the 4 ln x, because I need to let them get at each other to cancel each other out, since they're inverses. So that 4 would have to pop inside. So I would write it as that to the power 4. And as soon as you make it power 4, x to the power 4 can't be negative. So that's just ln x to the 4. But if you were stuck with that, if you were stuck with e to the ln x, which then, strictly speaking, should just be x, the same thing applies. Normally, if that was standalone, that's what it is. But if it's getting used as a multiplication, that means that's getting multiplied by that, that's getting multiplied by it, and that's getting multiplied by it. So if it happens to be positive, all's well. If it happens to be negative, they're all negatives, and the negatives would cancel out, so all would be well as well. So that's why you don't need to bother with those either for integrating factors. But anyway, in this case it didn't matter, because mu was just e to the ln just takes you back to x to the 4. So what that says is, if you multiply this by x to the 4, that should make that exact. So you try it. X to the 4 divided by dx. X to the 4 times that makes it 4x cubed. Whoa, look, there it goes. Look, x to the 4, derivative that, perfect. X to the 4 times that is x to the 4 minus x cubed. So the integrating factor made that exact. Now you know that that's exactly the derivative, it all depends how much you want to put down, that's exactly the derivative of, it was x to the 4 times y originally, before you used the product rule to produce the two parts. That's what's equal to this, which means that, again, dx to the 4y will be x to the 4 x cubed, splitting the differentials and then integrating, but quite often that integral, you miss this bit and just jump straight in with x to the 4, but since I'm doing it just now, so x to the 4y will be, and that's just up to 5, that goes up to 4, and don't forget the balancing constant at the end, and finally to get y, divide everything by x to the 4. So it'll be 1/5 of x minus 1/4 plus c over x to the 4. For the general solution, because I've still got a constant. If you want a particular solution, you'll give me some initial values. One last example, just to mention that business again, you'd look at that and you would say, oh, that's linear, so I'm going to do integrating factors. So you think, right, I'll divide that out. dy by dx minus, and that'll be xy equals x, and then you proceed to find the integrating factor. Well, don't forget, check if it's separable, because that would be quicker, and that would factorise. Look, dy by dx would be x plus xy. That's equal to x times 1 plus y. So you can separate it. dy over 1 plus y equals x dx. And I should have thrown in the integral signs before I carried on. ln of 1 plus y equals a half x squared plus c. So 1 plus y, escaping from the log, would give you e to the half x squared plus c. Notice e. The function e, no matter what you're putting into it, whichever way around, positive and negatives, is always positive. So I don't need that modulus sign anymore. And then finally, y is equal to this part, of course, there's that same business again, plus c in the power. That's the same as e to the half x times e to the c, so I'll call that something else, like a e to the half x squared minus 1 for the general solution. So even though it was linear, you could still just separate the variables. Oh, one other thing. Oh, I'll have to put this back down again. If that had been a homogeneous equation, in other words, there was no term that didn't mention a y, so that absolute constant term was missing, that's the homogeneous equation, all of a type, homogeneous, then even if it is linear, it can always be solved by separating the variables, obviously, because that would just pop over the other side. Because that must be made, if it's linear, of two parts, a coefficient of x and a y. So it must be separable. Even if there was something here which are just x's, they would just go on that side. You'd have something of x times a y. Even if there's a something of x underneath, it's separable. Oh, now that I've written down again, what would it have been if you did it the integrating factor way? Well, you'd have said this, right. That's xy equals x, right. This would be the derivative. This p of x, this negative x, is going to be the derivative of that e thing, that integrating factor. So that means I get the integral of negative x dx, which is negative a half x squared, which means the integrating factor, call it x or not, is going to be e to the negative a half x squared. And if you pop it in, sometimes you don't even pop it in, you just trust it and then just put in that times y on this side and that times whatever's here on that side. But I just like to write it in so you can see the pattern quite nicely. You can see that you've successfully made it exact. Well, there's something else here that's handy for doing this anyway, something else to mention. So there, having done that, you can see it was successful. I've not put the y in, because there's y, there's its derivative, there's that, and there's its derivative. Differentiate that, it stays the same, but gets multiplied by the derivative of the inner function, which is negative x. So that just comes down to the derivative of this thing, e to the negative a half x squared times y, equals this though, x times e to that. I think I'll just save a bit of time just by going vroom, vroom, whoom, and whoom, being the appropriate integrating noises. Get that over there a bit. E to that. Now, don't look at that and think, that's going to be integration by parts, because it's not integration by parts. If that was integration by parts, you're not going to whittle away that x. Whittling away that x means you'd want to differentiate that, which means the first thing you're going to do is integrate this, which you're not going to do. Well, you could do it by a substitution, or you could just do it by inspection. Don't forget to check if something happens to be an exact or just a multiple of an exact derivative. And that is, the derivative of this would be negative x. It's been multiplied by x, which means it's the negative of the derivative of that. So that side is just negative e to the negative a half x squared plus c. And then finally, take this across and divide. Now that's the same as that, so that will just come to negative 1, and that will be c divided by this. So if it's power negative underneath, it would transform to power a half on top, and that's the same answer as before. Before I called that constant a. It was that minus 1. There it is. Now, as if that hadn't gone on long enough, to finish off, here are 10 examples. I'm not going to do them. It's just in each case decide what's the appropriate technique. Will you separate the variables, or will you use an integrating factor? Remember, being linear doesn't always mean you're going to use an integrating factor. Sometimes it's quicker if you separate the variables, but you can do it either way in a case like that. So some of them will be either separate, some will be definitely just integrating factor, but some of the linear ones could be either, because obviously being linear, you can always use an integrating factor. This one, it's not linear, so it's separate. And of course the separation is, it's that times 1, so that would go across and divide. This one is linear, so you can use an integrating factor. But look at the nature of these terms. This has also got common factors in it, so you could also do it separable. If I do it, just put it down both ways. If I take those terms over, 6xy plus 12x, they'll factorise. They would factorise to 6x times y plus 2, and then that 3x squared can come across here, 3x squared. There it is, separable. You've got 2 upon x on this side, and you've got a y upon 2 to go across to the other side. It is linear, so you could use an integrating factor. If you were to do it that way, you'd rearrange it into the form of 3x squared minus 6xy equals 12x. You would do this. You'd have taken that across and divided it. So 6x over the 3x squared would have given you 2 over x. And 12x over that would have given you 4 over x. And your integrating factor would have been e to the integral of negative 2 upon x dx. Not linear, has to be separable. You'd take this over the other side, and then cos squared y would go underneath, and x would also go underneath as 1 over x dx. This one is linear. Well, that's sine x. That sine isn't the sine of y, so that's just a function of x. That's just a coefficient multiplying y. This is linear. There's no common factors, so this will be an integrating factor. That would be in front. In this case, p of x is sine x. So the integrating factor would be e to the integral of sine x. This one is linear. It's got y on its own. There's no common factors there. So this will be an integrating factor. Just get it into the appropriate form. dy by dx, and that'll be minus 2y, and throw everything else over the other side as 1 minus 2x. Integrating factor will be e to the integral of, and p of x in this case is negative 2. Or I could just put that 2 at the front. Should have put that down here. P of x equals negative 2. There you go. Obvious. That's not y on its own. That's a y to the power 5 and loads of other y's. That's not linear. That's separable. It's immediately separable. That goes under there, and the 3x goes under here. Dx on top. That bit might look linear, dy by dx, and then some function of y, but there's another mention of y over here, and that's not linear. So it's definitely not linear. This isn't an integrating factor. The only way you'd be able to do this would be if I can get a factorization to separate them, keep them apart. So what would that be? dy by dx would be, and I've got x squared, I've got x y squared plus x minus 2xy, plus 2xy, xxx. So you've got x times, and that's y squared plus 2y plus 1. Notice how you deal with that. Obviously the x stays here, but that would go underneath the dy. Quadratic, that factorizes. So this side here, this dy over that, you would use partial fractions then to integrate it. This is one that's both, because obviously it's linear. The only y term in this is a 3y, so you could rearrange it to get an integrating factor. But it's not worth it, because it's already immediately in a separable form, and that's always quicker doing a separable one. One general rule with separable ones are, though, try and leave all the constants where all the multiplying numbers, that is, where the constant goes. So when you do take this over, don't take the 3 with it. You would do dy over y plus 2 equals, and then that would be 3 over 2 times x plus 3 dx. You could use an integrating factor if you wanted, but it's just so obviously suitable for separation there. If you wanted to separate and to make it an integrating factor, to make it a linear equation, then you'd have to bring this over. So that would be a minus 3y. And that would leave a 6 over here. Then I'd have to divide by this over 2 times x plus 3. Notice that same term is applying there. Over 2 times x plus 3. And that would be your integrating factor. So, p of x would be negative 3 over 2 times x plus 3. And then the integrating factor would be e to the integral of this. And this one, straight away I can see I've got y on its own, so it's linear, which means if you wish, you can use an integrating factor. But you should really just check, first of all, whether it's separable, because these two terms have still got to go together here. So if I was to join them together, I'm actually going to bring this over here and write it that way. So that would be x squared plus x dy by dx. Bringing that over. Minus y equals, and that would be negative 1. Now there you are in its linear form. If you just take that across and divide, there's your p of x to get your integrating factor. But x squared plus x dy by dx would equal, take that across as y minus 1. Now you've got two perfect sides. Only x's, only y's. dy over y minus 1 is dx over x squared plus x. Notice for this one, that factorizes partial fractions, then logs. That's just a log straight away. So that's separated. But it was linear, so if you wished, you could have used an integrating factor. And that integrating factor, if I just put it down properly, that would be minus 1 over x squared plus x. Would be one where p of x equals negative 1 upon x squared plus x. This one, well, it's linear because there's only y on its own. That cost belongs to x, so it's just some coefficient times y. But I can't bring that across and have any common factors. There's no common factors here. So this isn't separable. This is going to be an integrating factor 1. Unless it's exact, of course, you may look at that and be tempted to think, oh, wait a minute, y, dy by dx, sine, cos, that wee minus spoils that. I can't just play about and make that both minus because then it's still wrong. So you'll need to rearrange this, but I'm not going to do it here. I'll do this in a couple of the other ones in another video just so you can check your answers to this. Now, if you're watching this, it means you've gone through all of that. Oh, and you're probably wondering, what are the solutions to these? Well, I'm not going to go through them. I will go through the last two, 9 and 10, but don't try and go through numbers 3 and 4, for instance, the two trig ones, because you'll find them quite tricky. In fact, number 4 is trickier still. That's the problem with calculus. You can put anything down and differentiate it. Throw any terms down you like, you can differentiate it. Not so with integration. Some get so difficult, even though they seem so simple when you write them down, that you have to use numerical techniques to try and get solutions to them. So I'll go right through numbers 9 and 10 in a separate video, mentioning some features about the final solutions, especially to number 9 where there's two different techniques. And it might look as if you get two different answers to it. But that's another time.